Okay, so let's do one more Coulomb's law problem where we have a continuous distribution of charge. Let's say that we have a strange thing, perhaps a strange thing, but a semicircle. Let's say that we have a semicircle, half a circle of charge, total charge, capital Q, radius of r, and we put another charge that we want to find the force on. We put a charge Q, little q, in the center of that semicircle. And I want to find the net force, the net electrical force on little q. Just as an aside, something that we're going to come across later is often when we talk about these large distributions of charges and what their force is on some small charge, we'll often just call that small charge a test charge. So let's say that we have a semicircle of charge total Q, and we want to put a test charge. We want to test what the force is, or later on what the field is, at the center. So we're going to put a test charge little q at the center and ask what the net force is. So how do we deal with this situation? What I need you to think about is to push pause right now and just ask yourself, how do you find the net force on little q? What are we going to do? How are we going to break it up into a situation that we can deal with? And we will deal with it in the typical ways we always deal with it when we have a continuous distribution. If I have a continuous distribution of charge, I'm going to say any one little piece of charge has a charge dq, and that will exert a force on the test charge, dF, which is equal to k dq times q over r squared. In this case, r is the radius of the semicircle because that's how far apart they are. And it is repulsive, assuming all these charges are positive. And yes, test charges are always positive if we call it a test charge. And the semicircle, whether it's positive or negative, we're just saying it's q, so we can just assume it's positive. If it's negative, we put a negative sign in when we plug in numbers. And then in order to find the net force on Q, so the net force of Q on Q, of the semicircle on the test charge, we're going to sum up all the dFs. We're going to sum up all of the individual forces due to the point charges that make up the semicircle. And what you need to think about is what changes. What changes as I sum up that F? K is a constant, dQ is a constant, Q is a constant, and R is a constant because we chose a semicircle, but the direction changes, right? I'm going to draw in a different dQ in a different direction, right? So if I have a dQ up here, it's going to have a dF down here, and that's going to have the same magnitude, but it's going to have a different direction. And so what's going to change is the angle, is the direction. But as we've seen before, we can just use symmetry in this situation and say that, oh yeah, for every dq above the horizontal bisector, there's a dq below the horizontal bisector, such that their up and down forces cancel and their horizontal forces add. So I've drawn that in with the gray lines here, right? There's for every force that comes from below the horizontal line, it's going to have a x component that points to the right and a y component that points up, as those little gray lines are that I drew. And then there's going to be an equivalent force from dq below that has a horizontal that goes along the plus x direction, and a vertical that goes opposite the vertical of the one above it. So the y components are all going to cancel, and the x components are all going to add. So all we need to do is take the x component of each df, and then the vector sum turns into a scalar sum. So let's go ahead and put in an angle, right? So the angle that I'm going to be interested in is in here. I'm going to call it theta, so that the x component of df, dfx, is equal to df cosine theta. So we can turn the vector equation into a scalar equation by saying everything's in the plus x direction if we write df cosine theta, so we don't have to worry about directions. And so I'm going to go ahead and fill in k q over r squared, just putting the constants in front, and we've got dq cosine theta. So we've got our typical problem here of we've got the integration variable is dq, while the thing that changes is theta. So we've got to find a relationship between dq and theta, which might seem a little different than something we've done before, but it's not really. We're going to find a relationship between dq and theta. So here I've redrawn the semicircle, and I've drawn the dq. Remember, we want to find a relationship between dq and theta. And I've drawn a little extra geometry on this picture. Remember, we have to use something like density. Density always comes up here to make these relationships. The charge dq has a width ds. But what is that width ds? How does that relate to theta? Well, we take the r vector, and the r vector must trace out an arc length, right? As we move through an angle, we can call it a small angle, d theta, is going to trace out an arc length such that ds is equal to r d theta. So that's the arc length. And remember that dq over ds, the charge of the infinitesimal point charge divided by the length of the infinitesimal point charge, is equal to the total charge of the arc divided by the total length of the arc. Now, I never gave you L, but you know what the total length of the arc is because I've given you R, right? So this is a density statement. Forget what I just said for a second. This is a density statement that I just wrote down, that the density of the point charge is the same as the density of the whole semicircle, the orange semicircle. And the density of the whole semicircle is the total charge divided by the total length, which is equal to pi r, right? It's half a circle, so it's not 2 pi r, it's pi r. So therefore, dq over r d theta is equal to q over pi r, and now we have a relationship between dq and theta because we've got dq is equal to q over pi r times r d theta, or just q over pi d theta. So let's go ahead and plug that dq into the equation above. So now the net force on, I never drew my test charge back in this picture, the net force on my test charge is kq over r squared times the integral of dq, which is now q over pi d theta, times the cosine of theta. So now again, whoops, this was a pi. I'm going to pull out all the constants. So we got k q over pi r squared cosine theta d theta. And the question is what are the limits of integration? In other words, what does theta go from and to? So we're now integrating along theta. And so the question is what is theta? And we're going from one end of the semicircle to the other. I'm going to draw something along the semicircle here. I'm going to go from one end of the semicircle to the other. And so now you want to think about what is theta. Let's put an axis. It's like if we call the horizontal theta 0, then we can maybe start from theta is minus pi over 2 and go all the way around to theta equals plus pi over 2. Whoops. I just did those angles in radians. If you don't like radians, you can say we're going from minus 180 degrees to plus 180 degrees. Somehow you need to put the thing on an axis and just say what angle are we going through. We're going through a 180 degree angle in order to do this integral. So now it's just a case of taking the integral of cosine theta d theta and plugging in the limits. So I just walked away from this for a second to help somebody declare for the major, and I forget where I left off and don't know how to go back. So we were taking the integral. We figured out the limits of the integral because we're integrating over an angle, so we had to figure out from what angle to what angle we were integrating. And then we just do the integral of cosine theta d theta. Now that's something that I've said in the past, that you need to know the integrals of x to the n. I haven't said you need to know the integral of cosine theta d theta, but this is something that you can easily look up. It's something that you should know at this point if you've done any integrals. The integral of cosine theta d theta is just sine theta. Then we plug in the limits like we've always plugged limits into an integral, and what you end up with is what we have here. So that's just an example of the force of a charge distribution on a test charge. And this is something that we're going to spend a fair amount of time with, is different kinds of charge distributions, and in particular symmetric charge distributions. But I do want to take this to the one step further of getting back to Newton's shell theorem, which is we can go ahead and we can do the force due to a ring of charge on a test charge little q and see that the net force not only points along the axis of the ring of charge, but we can figure out what that is. We've just done that with gravitational masses, so I don't need to redo that for the ring of charge. And then we can add up a bunch of rings that move outwards along the x-axis to make this whole thing a sphere. It doesn't look like a sphere the way I've drawn it, but we can make it a sphere of charge and add up a bunch of rings. And what Newton's shell theorem told us is that the net force due to the net force due to a shell is the same as if the shell were a point charge, not a point mass, but a point charge at its center. So the electric force between a shell of charge and a point charge q is kqqq over d squared, where d is now the distance between the center of the spherical shell and the point mass, and it's in the radial direction, still as shown. And the shell theorem goes on to say that if I'm inside this shell of charge, the net electric force is 0. And if I make this shell a solid sphere is a bunch of shells. And so if I'm outside a solid sphere of charge, then the solid sphere looks to any point charge outside the solid sphere as if it is a simple point charge with all its charge concentrated at its center, and still has the electric force that has the same form as Coulomb's law, kqqq over r squared, where r is the distance between their centers. So Newton's shell theorem holds for point masses and spherical masses, and point charges and spherical charges in the exact same way. So we know that the electric force between spheres of charge is kqqq over r squared, given by Newton's shell theorem, or you could say given by Coulomb's law, because a shell or sphere acts like a point. And Coulomb's law is for 2 point charges. So in summary, we've seen Coulomb's law for the force between 2 point charges. I've given you the values of the constants. And if you have a collection of charges, you just have to add up the electric force due to each of the charges. And if it's a continuous distribution, it's going to be an integral. For shells and spheres, we see that integral ends up being that when you're outside the radius of the shell of the sphere, they act like points. And inside a uniform shell of charge, the electric force is 0. That's the shell theorem. Next, we're going to talk about electric fields, because that's a really good concept to talk about electricity. But that's going to be for next time. You'll have to wait. Sorry. Although I gave you a little puzzle earlier, let me give you a joke now to finish up the day.